In this video, we're going to wipe out section 2.4, which is a library of parent functions. So we're going to identify and graph linear and squared functions, identify the graph cubic, square root, and reciprocal functions, and identify and graph step functions and other piecewise defined functions, and recognize the graph of parent functions. You know, just when you see a function, you should have a rough idea of what that graph is probably going to look like. So the first type are linear or squared functions. One of the goals of this text is to enable you to recognize the basic shape of the graphs of different types of functions. For instance, you know that the graph of a linear function, f of x equals some number a times x plus or minus some number b, is a line with slope m equal to a, or whatever is in front of the variable x, that will be your slope. And the y-intercept is 0, b, whatever this number is at the end, that is your y-intercept. The graph of a linear function has the following characteristics. The domain, remember those are the x values you can put into a linear function, that's all real numbers. The range of the function, that is where you are defined on the y-axis, that is also the set of all real numbers. The graph has an x-intercept of negative b divided by m, 0, and a y-intercept of 0, b. Remember, you can algebraically find the x and y-intercepts by, setting the other variable equal to 0 and solving for the one you're looking for. The graph is increasing if m is greater than 0, or that just means if the slope is positive, the function is going to be going uphill, left to right. And if the slope is negative, less than 0, it's decreasing. It's constant if the slope is equal to 0. That would just be a horizontal line. So here in example 1, writing a linear function. Write the linear function f, for which f of 1 is equal to 3 and f of 4 is equal to 0. What the heck are they talking about? You know this right here. F of 1 is 3 and f of 4 is equal to 0. Well, that's just a different way with the function notation of coming up with 2 points. Remember, to find a slope or to write the equation, we need 2 points at least. So f of 1 equals 3. That means there's a point, and when we plug in an input value, an x value of 1, out pops a 3. So 1, 3 is a point on our graph, on our line. The second one, f of 4 is equal to 0. Well, that's just another point. We put in a 4, out pops a 0. Now that we have 2 points, we can first use those to find slope. Change in y over change in x. So I'm going to come over here and write my slope. M equals, and I'm going to subtract left to right. 3 minus 0 is my numerator. 1 minus 4 is my denominator. So 3 minus 0 is 3, 1 minus 4 is negative 3, and if I divide those I get a 1, and I have a negative there, so my slope is negative 1. M is my slope, and that's equal to negative 1. Well, now, since I have the slope, and I have at least 1 point, I can write the equation for this line. Now, we do have 2 points. So we could use either of these, it does not matter. And actually, I'm going to solve it both ways just to show you that it works. So we're going to use this point-slope equation, y minus y equals m times quantity x minus x. Let's do it first with this point, 1, 3. So that would be y minus 3 equals negative 1 times quantity x minus 1. Or I can do it with the other point, 4, 0. Y minus 0 equals m negative 1 times x minus 4. Let's start with the one on the left here. I will distribute the negative 1. Y minus 3 equals negative x plus 1. And then I'm going to add 3 to each side. When I add 3 to this side, 1 plus 3 is 4. So there's my equation. If, on the other hand, you chose this other point, we'd have y minus 0 equals y. Distribute this negative 1, negative x plus 4. Exact same equation. As long as we have a slope and a point on that line, we can write the equation. And here we knew these 2 points. It doesn't matter which of those two we use. We get the same equation either way. Here we're going to talk about the squaring function, or f of x equals x squared. General shape is it's going to be a parabola. If it's positive x squared, it opens up. If it's negative x squared, it's going to open down. And let's talk about some other stuff here. The domain of the squaring function is all real numbers. Again, any x value that we can plug in from negative infinity to positive infinity, we can throw it in there and square it. Now remember, the range here is going to be a little different. The range is the outputs. If I put negative inputs in and I square them, the outputs are positive. If I put positive inputs in for x and I square those, they stay positive. So when you're squaring something, the answer is always positive. So the range is just going to be all the positive real numbers, or the non-negatives, from 0 to infinity. It's an even function. We have an intercept right at the origin, 0, 0. It's decreasing on the left-hand side. Here in quadrant 2, the function is going downhill as we look at x values from left to right. And then it's increasing from 0 to infinity. Once we get past the origin, now we're going uphill. It's increasing forever after that. It's symmetric about the y-axis. Here's the y-axis. If I pick a point over here, negative 2, 4, I can look at the reflection of that on the other side of the y-axis, and there is positive 2, 4. If we put in a negative or a positive 2, it doesn't matter. The output is always positive, and here it's the same, positive 4. Okay. Cubic, square root, and reciprocal functions now. Some basic characteristics of the graphs of cubes, square roots, and reciprocals are summarized as follows. The graph of the cube function, x to the third. Remember, x squared was sort of a parabola opening up. If, when we plugged in positive and negative x values, they were mapped to the positive y values, so our parabola opened up. Now, what happens if we put a negative number in the cube function? Like here, our function is x to the third. What if we do negative 1 to the third? Well, a negative times a negative times a negative gives us a negative answer. So it's kind of like we took this left side of the parabola and bent it down into the third quadrant. Positive x values to the third power will give us positive y values. Negative x values to the third power will give us negative x values. So it's kind of like we broke the parabola right at the origin and bent the left half of it down into the third quadrant. So the domain is going to be all real numbers. Any x positive or negative, we can put it in there and cube it. The range is also all real numbers. We can get negative outputs or positive outputs from the cube function depending on what we put in. It's an odd function. It has an intercept right at the origin. It's increasing across the entire interval. From left to right, no matter where we pick on the graph, as we go from left to right, we are always increasing, up, up, up. It is symmetric about the origin. So if I put in a positive 2, the output would be mapped up here to positive 8. If I put in a negative 2, it's mapped down to a negative 8. These points, let's just look at here, 1, 1, and negative 1, negative 1. They are reflections across the origin. The square root function, square root of x, has the following characteristics. The domain, the numbers we can put in, are non-negative. They're positive. We only put in positive x values. Negative x values over here are not defined. The range of the function is also non-negative real numbers. When you square root a number, only positive numbers pop out because you're only square rooting positive numbers. So our y values, our output values, our range is only positive y values. That keeps our square root function firmly in the first quadrant. We do have an intercept right at the origin, 0, 0. The square root of 0 is equal to 0. The graph is always increasing from 0 to infinity. Starting here, it starts out pretty steep, but it starts to level off. But it is always increasing, no matter how far over we go. And then we have the reciprocal function, or the fraction function, 1 over x. X is our variable. has the following characteristics. The domain is all numbers except 0. Remember, for 1 over x, what do we never want to divide by? We never want to divide by 0. So that is not part of our domain. Actually, at x is 0, we have an asymptote, a line that we will approach but never touch. Touching an asymptote is like dividing by 0. Odd function, it does not have any intercepts. It will never cross the x or y axis. It is decreasing on the left side from negative infinity to 0. We're decreasing and heading down. And we are also decreasing from 0 to infinity. You know, here we start on the left, we're going downhill, downhill, and then it starts to taper off, but we are always going downhill. And it's also symmetric about the origin. Now let's think about this here, this point 1. If we plug that in for x, 1 divided by 1 is 1. Let's get halfway closer, 1/2. 1 divided by a half is 2. How about 0.01? What if we get really close to the y-axis here? 1 divided by 0.1 would be 10. We'd be way up off the graph. Well, what about 0.001? 1 divided by 0.001 is 1,000. So again, we're real close to the y-axis. We'd have to go way up to 1,000. 1 divided by 0.00001. That's going to be 1, 2, 3, 4, 5, 6, 7, 10 million. 1 divided by this decimal, you know, we could get really, really close to the y-axis. You know, we'd have to go up to a height of 1 million. We can always get a little closer. Add another few zeros in there, add another decimal point with a few zeros after that, and that makes our number bigger and bigger and bigger. So we're never going to touch the y-axis, but we can get very, very close to it. The closer we get to the y-axis, the higher up our function goes. Now here's one you might not have seen in pre-calc. A step function. Functions whose graphs resemble a set of steps are known as step functions. The most famous of the step function is the greatest integer function, which is denoted by this. It almost looks like double absolute value bars. It's kind of like double absolute value bars, and we have an x in there. We can call that the greatest integer function or the step of x. So this graph of the greatest integer function, the step of x, has the following characteristics shown in the graph. The domain, all real numbers. Range, the set of integers. If we look, you know, left and right from the function, we're only defined right on the whole numbers, at 1, right at 2, right at 3. If we're anywhere in between and we look left or right, the function isn't there. It has a y-intercept at the origin and x-intercepts on the interval from 0 to 1. The graph is constant between each pair of consecutive integers. It jumps vertically 1 unit at each integer value. Another way to think about this function is the rounding down function. And let me blow this graph up a little bit. So remember, our inputs are on the x-axis. Let's go here between 2 and 3. Let's say I plug in 2.1. The rounding down function, or the step function, will round 2.1 down to 2. So that's where we are right here. 2.5, the rounding down function will round 2.5 down to 2. Let's get real close to 3. 2.8 will be rounded down to 2. 2.99999 will be rounded down to 2. So anywhere between 2 and 3, we are rounded down to 2. Right when we hit 3, we jump up to the next step. 3.0 rounded down is 3. 3.1 rounded down is 3. 3.2 rounded down is 3. Any number between 3 and 4 will be rounded down to the whole number 3. And even on the negative side, let's go between -3 and -4. Any number between -3 and -4 will be rounded down to the negative number 4, -4. So you could call it a step function or the rounding down function or the greatest integer function. You know, it does look like a set of stairs. So let's evaluate this step function. We have f of x equals the step of x plus 1. Now we're going to evaluate at a couple different x values here. F of -1 means we're going to do the step of -1 plus 1. Well, -1's already a whole number, so the step bars aren't going to do anything. That's just going to be a -1 plus 1, which is 0. Next one, 2. F of +2 equals the step of 2 plus 1. And again, 2 is already a whole number. The step bars aren't going to do anything. We just round that down to 2 plus 1 is 3. Now here we actually get to do something. 3 halves. F of 3 halves is the step of 3 halves plus 1. Well, let's think decimal. 3 halves is 1.5. And now these greatest integer bars are going to round us down from 1.5 to a 1. 1 plus 1 is 2. You know, now that I think about it, let's even check out a couple more that the book didn't ask us for. What if we wanted to find this of 2.6? Or no, let's make it 4.6. 4.6. So we're going to find f of 4.6, which is going to be the step of 4.6 plus 1. Well, these bars just round us down. Round down to the next whole number, 4. Plus 1 is 5. And here's a little graph to back it up. Okay, now remember the original, and let me back up here and see if I can grab this and just copy it. Okay, this was just the plain old step of x. And let me copy, and I can paste it right here. Paste. The one we just looked at in example 2 was the step of x plus 1. This was the step of x, the parent function, the original one. You know, it is going to have an intercept right at the origin. So if it's the step of x, we're going to intercept at right at the origin and then go over to the next whole number and then step up. And then over, step up, over, step up. Just like y equals 1x plus 0. I'd ask you, where does this y-intercept occur? Well, right at the origin, 0 would be your y-intercept. Same thing here. This is the step of x plus 1. So where are you going to cross the y-axis? Right at 1. So our y-intercept is at 1, and then instead of connecting the dots up like we're used to doing, we're just going to do steps. Over to the next whole number, step up. Over to the next whole number, step up. Over to the next whole number, step up. If I wanted you to graph y equals the step of x plus 4, you'd say, okay, well, I got to start somewhere, and there's my y-intercept. So I'm going to start right here at 4, go over to the next whole number, open circle, step up. Over to the next open circle, step up. You know, like that. You can get a lot from that number. That is your y-intercept, even on a step function. Example 3, piecewise-defined function. You know, these are like two functions in one. We have it in two pieces. We have the upper piece, which is used for x values less than or equal to 1 in this example, and we have a lower piece for values greater than 1. So, let's see what we got here. And actually, let's just look at this before we even think about it in pieces. If I asked you to graph this top piece, I'll do it in red, 2x plus 3. Well, that's a y-intercept of 3, and then it has a slope of 2. Up 2 over 1, up 2 over 1. I can back that up, go down 2, back 1, down 2, back 1. So here is the upper piece. And I got this done in red. Now I'm going to switch over to blue for the lower piece. Negative x plus 4. Well, that has a y-intercept of 4. 1, 2, 3, 4. And its slope is negative 1. Down 1 over 1. Down 1 over 1. Down 1 over 1. We're just going to go kitty corner through these boxes. Okay, so here is the function, two separate lines graphed. But on this one, we only want to see the red graph for numbers less than or equal to 1. So here is, and let me switch over to the black marker. Here's where we switch over at x is 1. So I'm going to come down this way. Okay, we only want to see the red line, the upper piece, this line 2x plus 3, for x values less than 1. So I can just erase this out of here. The red line only exists for values less than 1, or to the left of 1 on the x-axis. Now the blue function, we only want to see for x values greater than 1. Here's 1. We only want to see the blue function to the right of that. So I can erase this. Get that out of there. Got to fix my red piece. There we go. So for values less than 1, we're on the 2x plus 3 line. And then right when we hit x is 1, we want to jump over. Ooh, now that's a good distinction here too. This is x value less than or equal to 1. So at the end of the red line, we would have a solid colored in dot. For the blue line, x values greater than 1. It does not say or equal to. So here we would have an open circle. That's the distinction between the less than or equal to and the greater than. Again, this is just two functions, sort of chopped off at this x value. At x is 1, we're moving from one piece to the other. To the left of 1, we're on the red line. To the right of 1, we're on the blue line. Two separate lines that make up a piecewise-defined function. So now here's just a little summary of our parent functions. If it's a constant, it's just a horizontal line, like y equals 7. If you want to think about it like this, 0x plus 7. The slope is 0. Our y-intercept is 7. It looks like on this one it'd be maybe like 1.25. Y equals 0x plus 1.25. As we change this number, we're just moving the line up and down. It always has a slope of 0. The next one, y equals x to the first power. If it's a first power, it's going to be a straight line. If it goes through anywhere but the origin, we're going to add a y-intercept to the end, like a plus 6 or an x minus 3. As we put a number in front of the x, we change the slope. We can make it steeper or less steep, positive or negative. Oops. If we have an absolute value function, that's going to be a v-shape or a check mark shape. Again, it doesn't always have to hit the x-axis and bounce off. We could add a minus 3 to it, and that would just shift everything down 3. Or we could move it left or right by putting numbers in the absolute value bars with the x. The square root function always exists in the first quadrant. The square root of x is going to go up to the right. We could start moving that graph left or right by putting numbers under the radical with the x. Or we could maybe add a 1 after the radical to move us the whole graph up. Next we have the squared function. Remember, if it's squared, it's going to be a parabola shaped. First power, x to the first is always a straight line. X squared is going to be a parabola. If it's positive x squared, it opens up. If it's negative x squared, it opens down. The cube function, x to the third, is up in the first quadrant, down in the third. Again, it's kind of like we took a parabola and we just bent this side over the negative x values down into the negative y values. And here's another good point. If it's x squared, it's a parabola. If it was x to the fourth, it would also be a parabola, but it would be a little flatter on the bottom, and it would open a lot faster. It would go up quicker. If we had x to the fifth, it would also go up in the first quadrant, but a lot faster, and down in the third quadrant, a lot steeper. If it was x to the seventh, it would go up even faster and down even faster. So if it's an even exponent, it's a parabola opening up. If it's an odd exponent, it's up in the first, down in the third quadrant. The higher powers don't change the shape much. The reciprocal function, or rational function, 1 over x, decreasing left to right in the first quadrant, decreasing left to right in the third quadrant. We have our step function, or greatest integer function. Again, that's just rounding down. It looks like a staircase. So time for some practice problems here. What do we have? Oops, get that out of the way. For the first one, write the linear function that has the indicated values and sketch the graph. So here's a couple points. Come up with the slope. Come up with the equation. For number 44, evaluate the function at the indicated value. So you're just plugging in those values, round them down, and multiply by 2. The last one here is graph the step function. That should be kind of easy since we have the y-intercept right there. So let's pause the video, try the problems, and fire her back up. All right, 12. We want to write the linear equation and sketch the graph. So first we pull out our points. F of -3 is -8. So one point is -3, -8. F of 1 equals 2. That means 1, 2 is another one of our points. So let's find the slope. Y minus y over x minus x. 2 minus -8 over 1 minus -3. And for both of these, we add the opposite, and we get 10/4, which reduces down to 5/2. So our slope, our m, is 5/2. And now we can pick either of those points and plug it into our point-slope equation to come up with our equation. Which one should we plug in? -3, -8, or 1, 2? You know, I would lean toward 1, 2. Smaller numbers, easier to deal with. So y minus y sub 1 equals m quantity x minus x sub 1. So y minus 2 equals our slope, 5/2, times x minus 1. Let's distribute the 5/2. Y minus 2 equals 5/2 x minus 5/2. And to get rid of this subtract 2, let's add 2 to both sides. Or 2 with a common denominator of 2 would be 4. 4/2. 4 divided by 2 is 2. So we have y equals our 5/2 x. Negative 5/2 plus 4/2 is minus 1/2. And let me sneak over here and rewrite that a little nicer. Y equals 5/2 x minus 1/2. And they did ask us to graph it, so let's do a quick graph here. Our slope, our y-intercept is -1/2, so we'd be right about here. And our slope is up 5 over 2. 1, 2, 3, 4, 5 over 2. And we could do the opposite, down 5, back 2. 1, 2, 3, 4, 5, and back up 2. If we connect those dots, it's going to be something sort of like that. There's the graph of our line. Get on there. There we go. There we go. And now on to the next one, number 44. This we didn't have to evaluate. We're just we didn't have to graph. We're just evaluating. So 2 times the step of x. Remember, we're just rounding down. If we plug in -3, we just plug in a -3 there. That's already a whole number. We don't have to round anything. 2 times -3 is -6. So A is just -6. For B, 0.25. If we plug a 0.25 in there and round it down, that would round down to 0. 2 times 0 is 0. 9.5, 9.5. We would round that 9.5 down to 9. 2 times 9 is 18. Now the last one here, we have an improper fraction. 11/3. Let's make that a mixed number. How many times can we divide 3 into 11 without going over? Well, that'd be 3. And 3 times 3 is 9, so there's 2 left to get to 11. 3 2/3. So if we plug 3 2/3 in here for x and we round down to the whole number, that's just like chopping off the fraction. So we round that down to 3. 2 times 3 is 6. There we go. The last one is sketch the graph of the step function. The step of x minus 1. So that -1 tells us our y-intercept. We are going to hit right at -1, and then we would go over till we're about to hit the next whole number, and then we'd have an open circle, step up. Next whole number, over, open circle, step up. Over, open circle, step up. And you start to see the pattern pretty quick. There we go. And we can continue to the left, open circle over this way. Open, over, open, over. And there's our step function. The assignment, page 216, having a variety here. Number 4, number 32 are the even ones. Be careful with those. Again, check 29 and 33 in the back of the book. 32 is pretty close, so that will give you an idea if you got that one right. And that's 2 for a library of parent functions.